Hello, everyone. Thank you for attending today's webinar, where we will be giving a general overview of using near-infrared spectroscopy for mineral identification. My name is Lori Shelton Penizak, and I am a geologist and application specialist here at Spectral Evolution. In case you do need to leave a little early today, this webinar will be posted on our YouTube channel if you would like to watch it at a later time as well. So the outline for today's webinar will have us discussing the basics and giving an introduction to NIR technology. This section will really be for new users who have never used the technology before, or for people who might be interested in doing so. We will then take a look at Spectral Evolution's X series of field portable spectrometers that are used in the mining industry and for geological research and mineral identification. We will then take a look at some spectral data and the different kinds of spectral signatures that we might expect in certain parts of the spectrum, along with a section on minerals of interest in the mining industry. And we'll wrap up the webinar by showcasing a demo of our EasyID mineral identification software. So just a quick little introduction into who Spectral Evolution is and what we do. We are the leading manufacturer of high-quality, full-range UV, Vis, NIR spectrometers and spectral radiometers. We actually just had our 20th anniversary this past June, and we have our manufacturing facility just north of Boston here in the United States. So we do have other product lines that cover different types of industries and applications, such as hyperspectral applications, remote sensing, and vegetation. Of course, mining and geology, which we're going to be covering today. And we also have a lab photonics and calibration transfer product line as well. So if you are also interested in any of these instruments or applications, make sure to reach out to us, or you can even watch any of our other webinars on our YouTube channels. So let's discuss the product line that we offer for the mining industry. This is called the X series line, and it includes 3 different models of full-range spectrometers for mineral analysis. The Express here on the far left is going to be our standard resolution instrument, in that it has a standard spectral resolution of 2.8 nanometers in UV Vis, 8 nanometers in SWIR 1, and 6 nanometers in SWIR 2. The orange Explorer here in the middle is our newest high-resolution instrument that offers bit of a better spectral resolution, particularly in SWIR 1 and SWIR 2, which allows for better mineral analysis in that we can actually start to see more spectral features in our mineral spectra. And then finally here on the far right is our Expert, which is the highest spectral resolution field portable spectrometer in the world right now, that boasts a 1.5 nanometer resolution in UV Vis, 3 nanometers in SWIR 1, and 3.8 nanometer resolution in SWIR 2. So all 3 of these spectrometers are field portable in the sense that, maybe today you want to use it in the lab, tomorrow you want to pack it up, use it in the core shack, and then maybe you also want to put it in a backpack and take it to the field. So all 3 of these instruments are extremely rugged. They're built for field use. So this is going to truly allow you to bring your lab to the field, if that makes sense. Here is just a picture showing it being used in the field. You can see the spectrometer is here in the backpack. And so all you would actually be holding is the contact probe connected via fiber optic cable to the instruments to take measurements. Or maybe you want to use it in the core shack. A lot of people will actually put the instrument on a little cart, and as they're actually going down the core, they'll take measurements. I should note that one of the benefits of this technology is how fast you can actually take a measurement. So that's going to be in about 3 seconds to get your data. So we do offer a slew of different accessories that you can use with these instruments. Most people who are using it for mineral analysis, our most popular accessories are going to be our contact probes. We do offer 2 sizes that have different field of use. So we've got a 10 millimeter spot size and also a 3 millimeter spot size. Really, depending on what you need to measure and what your application is going to depend on which accessory you're going to use. All right, so let's get into what kinds of things you can do with a field spectrometer. By using one of these instruments, either in the lab, core shack, or in the field, you actually get instant information about the rocks at the outcrop, or maybe you're taking measurements in the open pit. So this actually allows us geologists to distinguish between minerals that have similar appearances, and it provides us with in situ data. So this cuts out the concept of having to send samples to a lab and waiting weeks or months for your data. Now, because of this, this actually provides more in-depth understanding of the processes that have actually altered these minerals. Now, spectroscopy is the study of the interaction between energy as electromagnetic radiation and matter. So radiation can be absorbed, emitted, or scattered by matter. Reflectance spectroscopy, however, can be defined as the technique that uses the energy in the visible range, which is 400 to 700 nanometers, the near-infrared range, which is 700 to 1,000 nanometers, and the shortwave infrared, which is 1,000 nanometers to 2,500 nanometers wavelengths regions. A lot of people, especially in the mineral industry, they will refer to the NIR and the SWIR range as SWIR 1 and SWIR 2. So if you do hear me using that verbiage, that's what that means. All right, so certain atoms and molecules absorb energy as a function of their atomic structures. So in the visible region, this is going to be caused by electronic transitions such as crystal field effects, charge transfer, conduction band transitions, and color center phenomenon. Much of this simply involves the release of energy when an electron changes energy levels in an atom. Now, absorption features in the SWIR region are different. They're going to be a function of the composition of the mineral. They are essentially a manifestation of energy absorption within the crystal lattice from the vibrational state transitions. So because these vibrational states correspond to distinct energy levels, the absorption features occur at well-defined wavelength positions. So those energy levels that define these wavelengths are a function of the size of the ionic radii of the cations bonded to these different molecules. So these bonds will vibrate at different wavelengths as a function of the length of the bond. So because the bond lengths between a specific atom and a molecule will be consistent, it's actually possible to predict compositions and compositional changes in minerals being analyzed by these wavelengths in these wavelength shifts. So the transitions between energy levels and compositional differences are going to be manifested by the absorption features at these well-defined wavelengths. So the common absorption features positions for minerals are listed here in this table. So each mineral has a distinctive spectral signature. They're composed of several absorption features, which is a function of composition, crystallinity, concentration, water content, and environmental considerations. Now, for mineral identification, that signature is going to be compared against characterized references for validated identification. So we'll see this done later on in the webinar. but you can actually use this by using a spectral library or a mineral identification software. Here is an example absorption spectrum of kaolinite. Now, these units for the horizontal scale are in nanometers, while the vertical scale is going to be percent reflectance. The absorption figure shown is a doublet with two minima or lowest points of the feature. Each minimum has a distinctive wavelength, which is a function of that chemical composition of that mineral. FWHM means full width at half maximum. So this can be used for symmetry determinations that are actually related to the crystallinity. So kind of going back to the spectral library talk, Spectral Evolution has a mineral identification software that you'll get to see a demo of at the end of the webinar. And we have 3 built-in mineral libraries, along with the option to actually create your own mineral library to match your target spectra against. And this can actually be used on a tablet or a laptop in real time, or you can do it as a post-processing function as well. Okay, so each mineral and mineral group have distinct spectral signatures based on the molecular bond of that mineral. They can have doublet features, singlet features. Those features can be sharp or they can be broad. Here is an example table here on the right outlining the different types of features that a lot of common minerals will actually expect to see. So for example, at the 1400 nanometers where you've got water and OH bonds, these are just some of the common minerals that we see that have different types of features. So alunite, for example, will have a doublet there. Illite will have a sharp feature. Quartz will have very broad features. And then things like hematite you'll actually see those minerals in the visible as well. All right, so there is an abundance of information that can be gained from the visible region of the electromagnetic spectrum. This is one of the features that does make full-range spectrometers so valuable. So the figure here is going to show some of the cations that are recognizable by color and corresponding minerals. So although the visible range is constrained from 300 to 720 nanometers, there is additional and complementary information in the near infrared, which is the 700 to 1000 nanometer region. For example, chlorites are more detectable in the visible range because there is less interference from other species compared to that in the SWIR range, where their signal is usually low unless those chlorites are the dominant phase. The nickel cation has also diagnostic features in the visible range that can be detected in nickel laterite deposits and correlated to the ore zones. Chrome in kimberlite minerals, such as chrome dioxide and G10 garnets, make spectroscopy invaluable to the identification of indicator minerals. So manganese is also detectable through these features in the visible range. Garnets, pyroxenes, olivine, selected iron and copper oxides, hydroxides, sulfates, and for heavy element carbonates, an NIR major absorption feature is going to be seen. So iron oxyhydroxides have many distinctive features that allow them to be discriminated from each other. This allows a discrimination of pH zoning, for example, and this is something that really hasn't been easily done before this type of technology. Rare earth elements have very distinctive signatures in the visible region and can be seen in the figure here. Rare earth minerals include such species as bastnasite, monzonite, and xenotime. Now, I'm not going to go through all of these, but this slide and the next slide that I'll show is going to showcase the different mineral assemblages that can be seen in the SWIR regions for different types of deposits. One big one being intrusion related, where you've got all kinds of different types of alterations that have their own distinct mineral assemblages to be expected. And so you're going to be looking for alteration patterns and spectral shifts in these minerals to identify, where exactly you are in that ore zone. Same thing with high and low sulfidation, epithermal, VMS, and more. So the SWIR method does not detect minerals per se, but the vibrational energy of the chemical bonds between atom and molecule in the octahedral layer of that compound. So this gives more flexibility in detecting these amorphous materials. So, therefore, it's possible to detect SiOH bonds and look at amorphous silicas such as opaline phases. Now, SWIR is also very sensitive to water, which will be illustrated in a later section in the webinar. So this is particularly valuable when tracking fluid migration through a deposit. So the common molecules detected here are going to be water, OH, carbonates, NH4. So selected sulfates are seen when an OH bond is present, as are phosphates. Other important information that can be obtained in the SWIR range is chemical substitution, crystallinity effects of water, paragenesis, and temperature. The ability to discern these compositional differences in mineral groups that have solid solution substitution is extremely useful. So some examples here are going to be the carbonates, amphiboles, chlorites, your white micas, tourmalines, smectite clays, alunites, all of these which exhibit wavelength shifts with cation substitution. So let's actually take a look at some examples of these minerals and mineral assemblages and their spectral signatures. So the spectral plots you see here, spectral plot A is going to be for alunites of different compositions that range from top to bottom. So if you're looking here in the region right here, you'll see this line. So this is going to showcase that compositional change from top to bottom, from calcium to sodium to potassium to the NH4. So you're going to note that the diagnostic feature ranges from 1495 nanometers for calcium to 1460 nanometers for NH4. And then in plot B, this is going to show the diagnostic wavelength shift that occurs at the 2330 nanometer range for magnesium chlorides. So from top to bottom, you're looking at the 2330 nanometer range for magnesium, shifting all the way down to 2350 for iron chlorides. Now, the carbonate group here in plot C, these minerals show a significant shift with the different cation compositions, ranging again from top to bottom. So this is going to show your aragonite, which is going to be calcium-based, dolomite, which can be either magnesium or calcium-based, calcite, rhodochrosite, which is magnesium, strontianite, magnesite, cerussite, which is going to be a lead carbonate, siderite, which is going to be iron-dominated, anchorite can actually be iron or magnesium dominant, malachite, which is a copper carbonate, and azurite, which is also a copper carbonate mineral. All right, so iron oxides, hydroxides, oxyhydroxides, and sulfates are very important not only to the precious metals exploration, but also in the determination of oxidation states and acid drainage creation potential. So these can actually be used in the field to provide approximate pHs in an environment, especially along a stream, as shown here in this figure. Now, the three most common iron minerals encountered, especially in gold and copper deposits, are going to be jarosite, goethite, and hematite. So the plot here on the right is going to show spectral profiles and wavelengths for these minerals in the visible range, where most of their diagnostic features occur. The emission features are most consistent and reproducible with their, these absorption features shown. Now, these features all have a range, and they occur usually as mixtures of each other, and therefore the wavelength range is more applicable than, defining them. So, for example, goethite is going to essentially be seen greater than 900 nanometers. Hematite is going to be seen less than 900 nanometers. Now, the iron sulfates are going to be very useful to help in determining pH of their environment and potential acid drainage factors. So they are plotted here in plot B for the visible range and plot C for the SWIR range. And these include schwertmanite, jarosite, cochromite, and melanotrite. Except for jarosite, they're all going to show mostly water features in the SWIR. So a full-range spectrometer is therefore essential for their definitive identification. All right, so aluminum content of illites. So this is a very popular, very important application here. These can be estimated from the 2200 nanometer absorption feature, which is going to be shown here with the line going horizontally. So essentially, this application is going to be very good for deposit-specific correlation, in that when illite, cerussite, and muscovite alteration is present, there's going to be higher amounts of aluminum apparently associated with the ore zones. So with this application in particular, we are going to be focusing on how this feature at 2200 nanometer is going to be shifting to the left or to the right, and that can help us decide what type of white mica we have. All right, so degree of crystallinity can be determined from the change in the profile. So using, for example, a calibration data set for comparison. So this is where something like EZID would really come in handy. So you're going to note here, again, we're going to be looking at the 2200 nanometer feature, but also this zoomed in portion here is going to be in this 1400 nanometer region as well. These two regions here are essential for kaolinite. And what you're going to be looking for is you're going to see how that kaolinite doublet in the 2200 nanometer region actually softens and broadens. So as we go down, we're at the very top, we've got a very sharp defined doublet here with kaolinite. As it softens and broadens, if you compare this very bottom feature to the very top, this is a lot broader, it's not as sharp, not as well defined. So this change in profile, this can actually essentially tell you you've got a well-defined minimum to a shoulder, and you can see how the ordering decreases. So if you're looking for the change in profile here, this can actually be mathematically defined, and you can even use it as an index. So you'll see later on in the demo, we actually have a kaolinite crystallinity index scaler that I'll show you. So this is actually a function of random and sporadic filling of the metal sites that are in that octahedral layer of the kaolinite mineral. So empty and random sites are going to end up being what actually decreases order, and therefore also decreases the sharpness of the profile as you go down. A very important series is going to be the one from montmorillonite through to muscovite. So this goes through mixed layer smectite, illite, and illite smectite to illite. So if we're looking at the very top here, again, this is montmorillonite, and you will notice how the change in this 2200 nanometer feature shifts, and you will also notice how the 1900 nanometer feature in the montmorillonite essentially is gone by the time you get to illite. So as we go down here, again, you know, this is going to be montmorillonite to muscovite into a mixed layer smectite illite, illite smectite, and then finally illite. So this plot here that we showed, it's essentially going to just summarize the species in the series, and it shows the information that can be gained by the wavelength shift, indicating the change in aluminum content. So this is actually the most complicated series commonly worked with in alteration systems, because you've got this change in water content, you've got the change in profile shape, and even the wavelength. These are all going to be subtle between the different species in the series. And, you know, I mean, they can be difficult to distinguish, especially in person, and can really only be differentiated by comparing them against references. Again, where those spectral libraries are going to come in handy. So profiles also give information related to paragenesis and indirectly temperature. So broad, open absorption features coupled with large water features, such as those found in smectites, zeolites, and opaline silica minerals, these are going to indicate the ambient to low temperatures from low energy environments. So when you're looking in this plots, essentially as the profile sharpens and it becomes well defined, for example, in muscovites, pyrophili, epidote, dickite, the temperature of formation increases. And so that crystal lattice actually becomes ordered in a high energy environment. So if you're looking here, plot 15 here on the left, so this is actually going to show change in profile. So these are going to be as a function of ordering in the crystal lattice. So again, you've got from broad low temperature smectites all the way to high temperature mica and pyrophilite down here at the bottom. So you can see how, you know, this feature here, this water feature, and then also your 2200 nanometer feature has changed. So in plot 16, these are going to show different water sites from, so if we're looking at 1900 nanometers, you're looking at this feature right here. So it's going to show, you know, the water sites from channel water in beryl into molecular water in gypsum to zeolite channel water to finally, this is, you know, inner layer smectite water. The very bottom here, this is going to be surface water. So you can actually see, if we're focusing just on this 1900 nanometer feature, in each different mineral, your water site is going to change, and so is the profile and the broadness of that feature. All right, so now that we've kind of went over the basics, what to expect, what these, you know, different spectral features are going to look like for different species and different mineral assemblages, let's actually move over and have a real-time demo of our EZID software. All right, so before I start going over the actual analysis of some examples, I just kind of want to introduce the software as a whole. So this is the EZID mineral identification software. Over here on the left in this box is where all of your data is going to be stored, whether you're taking it in real time or if you're doing post-processing, you would just load the data in. This far right box right here is the selected library, the spectral library that you choose to do matches with. Here in the middle, obviously, is the plot. So I can actually make this screen bigger if I want. And the way this works is the red line that you see is going to be the spectral data of the built-in libraries. The blue line is going to be your target spectra. So what you're actually measuring. So the software is comparing the blue, which is what you take, to the red, which is the built-in library spectrum. Over here to the far right, this is going to be the mineral scalars. So these mineral scalars are just kind of a handy tool for us geologists to have. Just kind of makes our life a little bit easier in the sense of you can really find out, a lot of geochemical information for, these different minerals. So you can figure out temperature of formation, you can see wavelength shifts, you can get that kaolinite crystallinity index I was talking about earlier. So these are very important to have. And then at the bottom here, this is going to be your actually match analysis. You can set it up to either match the full spectrum, or most realistically, you're going to have mixed minerals. So you're going to want to be able to unmix the spectral features as well. So if I wanted to focus in on the 2200 nanometer region, if I right click, add a region there, now the software is only giving me the match for this specific region that you're interested in, not necessarily the match for the full spectrum. So now that we went over that, let's just kind of go over the, realistically kind of what you can get with this. So this first example I'm showing you, this is an illite. So I wanted to kind of show a white mica example. So with white micas, if we remember back in the presentation, the area that you're going to be focusing on is this 2200 nanometer region. So I'm going to leave this green region here, and this is going to be correlated to the ALOH bond. So if I look over here in my scalars, I actually have an ALOH wavelength scalar that's going to tell me where that actual absorption feature is centered at. So it's telling me at 2198 nanometers is where my ALOH is centered there. With white mica in general, for that application, there's two scalars that you're really going to focus on. The ALOH scalar, and then also the ISM scalar, which is referred to as the illite spectral maturity scalar. So in particular, the ISM scalar is used to essentially track geothermal gradients. And so it's done by detecting the mineralogy and reporting this scalar. So for example, smectites will convert into illites with increasing metamorphic grade. And so these are then converted to muscovite and other true micas. So those subtle geothermal trends are easily detected within these white micas, and they can be mapped with this scalar. So you can have to imagine as illite converts into that true mica, this is going to track the illite dehydration process, which is why whenever if you see here, it actually shows the mathematical equation there. So D, so that means depth. So that's going to take the depth of the ALOH feature and divide it by the depth of the water feature. So when we talk about illite dehydration, that's what it's mapping. Now, true illite is going to have an ISM score from 2 to 4. So if you get a value here that is below 2, that's going to indicate that whatever white mica you might have in there, this is actually more of a smectite. So it's going to indicate if you have a value less than 2, I've got a smectite there. If I have a value above 4, that's going to be an indication of muscovite. So in this example, there's kind of two things we want to look at. The value, so 2198 of the ALOH feature, but also my ISM score. I've got a very high ISM score of 10.70. So even though this library is trying to tell me that it's illite, if you look at these scalars, this is telling me that truly that white mica has dehydrated, and this is probably more of a sericite muscovite. Whereas if I look at a different example, so we're going to look at a completely different illite here. If we look at this 2200 nanometer feature, not only does it visually look different, so if I zoom in here, I'm going to click back to the previous illite, and I want you to watch how that 2200 nanometer feature changes visually. So it's deeper, it's shifted quite a bit. So that's going to indicate that this is a different type of white mica. So if I look at the ALOH value of this illite now, we are actually centered at 2209 nanometers. So typically, whenever you're tracking the shift of these, it gives a good indication where you've actually got maybe a high aluminum white mica, or maybe you've got more of a magnesium iron dominant mica. Now, if you notice, remember we talked about the ISM score. Our ISM score of this illite is actually less than 2 now. So this would indicate to me, if I was, going down the core or taking measurements, this would indicate that this white mica is actually more of a smectite species. So that's essentially how you use the identification tool. You can see here the mineral scalars are very important. One thing that I mentioned also in the webinar, I talked about the kaolinite crystallinity index. If you are trying to track, that change in order of the kaolinite, this is that crystallinity index that I was talking about. So, if you're interested, maybe you're already using this technology and you just kind of want a software that's going to help you out with this. This is a great software tool to have. Like I said, the mineral scalars make, especially myself as a geologist, makes my life a whole lot easier, because this automatically gives you the information that you need. Whereas back in the day, you had to go in and zoom in and physically look and see where these features were centered at and do the calculations yourself. So this just kind of makes my life a whole lot easier. Okay, and so to conclude this webinar, you can see that our ORX series of field spectrometers, these can essentially provide you with a great tool for exploration. So depending on, you might not necessarily need the highest resolution spectrometer that we offer, but even the standard resolution one does the job. And the beauty of this type of technology is it is non-destructive. So you don't have to go out and prepare samples, send them to a lab, wait on results. And also the good thing is it's portable. Again, we kind of talked about you can use it in the lab one day, you can take it to the core shack, you can put it in a backpack and take it to the field if you want. And once you're actually taking your spectral data, this data it makes it easy to distinguish and interpret mineral spectra. And that's done by using our EZID software, which is going to allow for, better understanding of these minerals. We kind of talked about, that change in white mica composition. And so it can really help you with the understanding of your deposit. So thank you so much for attending today's webinar. If you do have any questions, my email is listed here. We will be sending a follow-up email to everyone as well. So if you can think of any questions, make sure you reach out to us, let us know. Definitely follow us on LinkedIn. And again, if you're interested in any of the other webinar videos, visit us on our YouTube channel as well. Thank you very much.